And I'll tell you about more symmetries, different anomalous insights into quantum phases of matter. So let's see. So let me first say a few words about the general problem. One of the central problems in modern physics is the study of quantum many-body systems. So they cover a wide range of physical systems, ranging from naturally occurred materials, which are traditionally associated with many-body systems in solid-state systems, to more engineered systems such as quantum Hall, or the more recent popular systems of stacked atomically thin 2D materials, van der Waals materials, which can be twisted and make all kinds of interesting things happen. And also even artificial systems, that man-made systems such as cold atoms, Rydberg arrays, or even super tiny qubits. Okay, so these systems are interesting and at the same time difficult to study because oftentimes the degrees of freedom inside these many-body systems are strongly interacting. And exactly these strong interactions that lead to a rich variety of collective behaviors. Okay. And as theorists, we are really good at dealing with non-interacting problems and taking into interactions by perturbation theories, which work well when the interactions are weak. And that's why we have a good theory of metal. But when interactions are strong, we need new tools to treat strong interactions. So this brings up two kind of motivating questions for what I'm going to discuss today. The first one is really the need to have tools to constrain the behavior of interacting systems, interacting electrons, especially when in the regime when perturbation theories may not work. And second motivation is just to have a better understanding of the very intricate quantum correlations and entanglement structures that are inherent in these complex many-body states, which are being observed and even made across the different platforms. Okay. All right, so with that motivation, let's now delve in a little more. Oops, something happened. Try to fix it in real time. Let me just. Right. Okay, so suppose you're given some Hamiltonian of a many-body system. One of the first things that you might want to ask is what the spectrum, energy spectrum looks like for this Hamiltonian. And especially what the energy spectrum looks like near the ground state when energy is very low, because that's what determines the behavior of the system at low energy and low temperature. Okay. And broadly speaking, two kinds of behavior that you can observe in the spectrum. So the first class is what's called a gap system, when you have a small number of ground states separated from the excited states by a finite energy gap. Okay. And within this class, there are further two sort of scenarios. In one case, you have a unique ground state, and this is case of, for example, a band insulator. And in the second class, you have somewhat more interesting behaviors we have with robust degenerate ground states. And this is the case for spontaneous symmetry breaking or the more exotic logical order states. And if there's no gap, then you just have a continuum of energy levels near the ground states. And that's the case for metals and quantum, for example, quantum critical points. So to better understand this kind of a basic dichotomy of a quantum many-body system, turns out that it's very useful and very insightful to just think about the ground state itself. Okay? It turns out we can learn a lot but just by looking at the ground state. So the simplest, arguably, I mean, according to my own criteria, simplest ground state of a many-body system that you can think of is the one that where each individual degree of freedom, each particle is bound to some, for example, atomic orbitals. They're just localized, they don't talk to each other. Mathematically, we say that this many-body state is a product, is a tensor product of each individual state, which are localized. You can also say that this is just a Slater determinant for electrons of atomic orbitals. Okay. This is a very boring state. There's no correlations of any kind. There's no entanglement of any kind. Okay. But we can make it a little more interesting by evolving this very simple looking state with a Hamiltonian of local interactions. We just allow the degrees of freedom to interact with the neighboring ones for a short period of time. Okay. And pictorially, and obviously this is motivated by quantum thinking, we can think about the effect of this finite time evolution in terms of this kind of quantum circuit where each of these blocks represents the local interaction between neighboring degrees of freedom. Okay. So this way you can build up some amount of correlations and entanglement between the different degrees of freedoms, but not too much. So we generate short-range correlations and entanglement through this sort of time evolution under a local Hamiltonian. Okay, but this is still fairly simple and very limited amount of entanglement. And we'll say that anything that you get this way is a trivial, uninteresting, featureless, whatever you want to throw on it. Okay. And sometimes I'll say this is short-range entangled. Okay, and you can easily convince yourself that if you have such a state, then it exactly corresponds to the simplest scenario in the energy level diagram, where you just have a single ground state, separated from everything else by a gap. All right, so once we know what's trivial and uninteresting, then the opposite of that is non-trivial and somewhat more interesting. Okay, and we'll just call anything that is not of this form a non-trivial many-body state or long-range entangled state. All right, so obviously this is not a particularly informative definition because I've just defined long-range entangled state in terms of what they are not. I haven't really told you what they are. Okay. And turns out it's a complicated question, as you probably already learned from Tolstoy, that all the trivial states are like, that's by definition, but each non-trivial state is non-trivial in its own way. Okay. So the task is to figure out a useful way to think about these non-trivial states. Okay. That's first of all. And turns out that symmetries and anomalies will be of great help in this task. And second, we would like to have some kind of indication of where you can possibly find this kind of long-range entangled state. If you can say a certain system cannot even possibly have a short-range entangled ground state, that's already somewhat useful. Okay. So that brings me to the one of the cast of characters, the anomaly. So of course there's global symmetries, but I'm sure that's somewhat familiar to everyone. Even though that notion of global symmetry is evolving quickly these days, I'm sticking to the notion of global symmetry in whatever you learned from introductory quantum mechanics. Okay. But anomaly is somewhat less familiar terminology. Might sound fancy, but turns out that this is something that we all learned in the introductory solid state course, probably undergraduate solid state physics. Okay. So what we learn in the introductory solid state physics course is that we can describe insulators and conductors using band theory. Okay. In band theory, you can have an insulator if you fill all the valence bands. And that means the number of electrons per unit cell has to be the same as the number of valence bands, which are integer. Therefore, electrons in the crystalline material can form a band insulator only if the number of electrons per unit cell is exactly an integer. Okay. So here a short example where you fill exactly one valence band, and that means you have one electron per unit cell. And if you have the number of electrons per unit cell smaller than one, or not integer at all, then some of these valence bands, the top one, will be partially filled. And we know from band theory that we get a metal. Okay. So from now on, I'll call the number of electrons per unit cell the filling factor. All right. Okay, so
Spin.
Hmm?
You ignore spin.
no, I'm just counting everything, but it doesn't really play an important role in this case. When I say that, well, it can get a little bit complicated, but when I say failing, I include all the electrons spin up and down.
And you need two of the unit cells to fill that.
It's still integer,
Okay,
I guess.
the difference between 1 and 2.
Yeah, so if we have spin, then we need to count the spin degeneracy. But here I'm not considering the spin symmetry. That is that's not really important on this slide. Okay, so now the point is that even though we can easily understand this statement in band theory, this statement actually goes beyond band theory, which is about non-interacting electrons. We can actually have a somewhat generalized and refined statement, which holds even when you have interactions between electrons. Okay, so let me just give the statement. The electrons in the crystalline material can form a featureless or a trivial insulator in the sense that we just discussed, only if the failing is an integer. Okay. And if the failing is a fraction, then the insulating state either has to break some symmetries or has to be long-range entangled. Okay, and here there's no assumption about the form of electronic interactions as long as they are local, they're short range. So the Hamiltonian for a system could be very complicated, but this statement still holds true. So what's really important here are the symmetries. We need translation symmetry, right? Otherwise, we cannot even talk about unit cell. We need charge conservation just to count the number of electrons. And importantly here, we have this condition of failing. So this is an example of a kinematic constraint. Kinematic means that it doesn't really depend on details of the interactions which are associated with the dynamics of system. Instead, it is about the structure of Hilbert space, the global symmetries, and the structure of the Hilbert space. Okay, I think what happens that my Zoom is keep updating, and every time it's causing this to quit. Hey. All right. So you can see from this example that the anomaly is a kind of a statement about obstructions of having a trivial state. Okay, just under certain very general microscopic conditions, symmetries and certain structures in the Hilbert space, it's just not possible to have a trivial state, and there's no assumptions on interactions or the formal Hamiltonian as long as they are local. So there are many other examples that are actually quite common. One example that we encounter in the subject of quantum magnetism is also called the Lipschutz-Matisse theorem, where you have a spin 1/2 electron per unit cell. So the failing is, I guess, 1 per unit cell, but you have spin 1/2. But if that's the case, again, a trivial state is excluded just by more or really the same reason. The other place where similar set of constraints show up is in high-energy theory. Actually, historically, this is where the anomaly was first discovered. And a concrete example is a 3 + 1, four-dimensional wire fermions, single-handed wire fermions. Oh my God, this is again. Wire fermions, single-handed wire fermions in 4D, and the U1 symmetry, the charge conservation of this wire fermion is anomalous. All right, so I'm going to use this kind of kinematic constraint to say something about interacting systems and share some light on the structure of correlations entanglement in many body states. So that will be first part of the talk. A more formal way to characterize anomaly, if you ask how these things are really proved and derived, I haven't told you how they are actually proved, is to think about what theorists like to call gauging the symmetry. For experimentally, this is just hooking up the system with leads and wires. That's gauging the charge conservation symmetry. But theoretically, a more convenient way to think about gauging is to imagine you act symmetry transformations, which were supposedly global, you're supposed to just do the same transformation over the entire system. But now to gauge it, you want to be able to do it differently in different parts of system. Okay? For example, you want to do U1, U of 1, some operation in this region, but you may want to do a different operation in a different region, etc. And you apply position-dependent symmetry transformations to their system. And this is really formally known as coupling to a background gauge field. Anomaly arises as some subtle quantum effects when you try to couple your system with a nice global symmetry to this kind of background gauge field. And this kind of thinking leads to anomaly, first of all, conceptually leads to anomaly, but also it kind of inspires a new class of observables, which having to do with applying symmetry partially to a system, which I'll discuss later. And by the way, please feel free to interrupt me with many questions. And I guess I'm gonna have many interruptions of Zoom along the way. We'll see how that goes. All right, so, okay, so now the first part, I'll tell two stories about how to use anomaly to constrain and uncover novel facial matter. Okay, any questions before I move further?
Have you defined what anomaly is so far in this language?
I have told you, I have defined anomaly as obstructions of having trivial states as a kinematic constraints coming from global symmetry and certain structures in the Hilbert space. And the other definitions is obstruction of gauging the symmetry, but I prefer the first definition. Well, there are symmetries and we don't know how to gauge. All right, so the first story that I like to tell is about interacting electrons in 2 dimensions at fractional filling. Again, filling counts all the electrons, all the degrees of freedom, internal degree of freedom, Valley or spin. But let's just, to keep notation simple, I'll just write C, the annihilation creation operator, without any internal indices. So the problem that I'm thinking about is electrons moving on some lattice. Doesn't really matter what the lattice is, and at fractional filling. Okay, the translation invariant Hamiltonian, which usually contains some kinetic energy, hopping of electrons over lattice, and there are some density interactions. There might be some other interactions that are not spelled out explicitly here. And now assume that the interactions are dominantly repulsive. So I don't have to talk about things like superconductivity. Okay, so let's just contemplate what can possibly happen to such a system. If the interactions are very weak, the kinetic energy dominates, then we know we are going to have a metal. This is what happens when the bandwidth overwhelms the strength of repulsion. Now, if you go to the other limit, when the interaction dominates, then electrons, they want to kind of become more localized to minimize the repulsion. And oftentimes they just form a sort of a generalized Wigner crystal or Wigner mod crystal, where they arrange themselves into some pattern to minimize the interaction stress, the interaction energy. And in this pattern, the unit cell is enlarged because we have a fractional filling. Okay, so these are well understood and familiar facial matter. And actually, this kind of state has been observed in 2D materials, the twisted TMDs. So a natural question when you look at this kind of diagram, phase diagram, is whether it's possible to melt this charge order, meaning that this charge order might be unstable towards quantum fluctuations, but the system remains insulated. Okay. So what if the ground state is insulating? So it doesn't really have a Fermi surface, everything's still kind of gapped, but you don't break you don't break translations. And if that happens, I'll call this a quantum charge liquid. You might want to call this a solid compared to liquid. Okay, so of course there are many ways to approach this question. You might want to just pick Hamiltonian and study the phase diagram. But the approach that I'm going to take here is a somewhat different approach, where I'm not going to solve any Hamiltonian. I'm going to try to say as much as possible just from general principles. So this is in the spirit of bootstrapping. So I'll just call it bootstrapping, quantum charge liquid. And of course, there are, if you don't put any further conditions, there are going to be too many possibilities. So we like to think about what's the simplest possible kind of quantum charge liquid that you can possibly realize in this sort of systems. So I want to have some notion of minimum quantum charge liquid. And here there are different ways to define what you mean by the simplest or the minimum. So there's a question of how do you measure the size or the simplicity of a quantum charge liquid?
It just
sure.
So, but by chart, still have a latest, right? So by liquid state, you need the some correlation function decays, or doesn't have
the correlation function decay exponentially because of the energy. Yeah. Right.
But there's the density correlation.
Yeah, it's so the density correlation will be rather structureless. There will be no peak at any finite moment. Anything like this. You'll see some kind of peak at momentum zero, but there's no other structure. So it doesn't break the lattice. Despite having lattice, okay, so it probably has a lattice symmetry, right? Whatever lattice symmetry that will impose on you. But other than that, there's no further structure.
The symmetry, well, it imposes rotational symmetry.
Rotational symmetry, but there's.
So it may impose translational symmetry.
Yeah, of course, right. So I'm assuming that rotation symmetry and translation symmetry are all preserved.
Translational symmetry continuous or discrete?
It's a discrete lattice translation symmetry. And the point you just said, the lattice translation symmetry is not broken further in this state. So whatever the lattice you start with, we have the same lattice translation.
There's no brag peaks except.
There's no brag peaks.
Yes.
Yeah. Okay, yeah, that's a better way to answer. All right. So to measure the size of this quantum charge liquid, the choice I'm going to make is to count the number of ground states under periodic boundary condition. Motivated by this kind of picture that these sort of phases are characterized by degenerate ground states. There are two reasons to justify this. First of all, this is now for the experts. The torus ground state degeneracy is equal to a number of anion types, which is some universal characteristics of this phase. And also, this number is accessible in finite size numerics, which is quite common in studying this kind of problems, for example, exact diarization. So the result that we are going to derive, assuming this notion of minimal quantum charge liquid, could have some implications in numerics. Okay, so let me first give you the result. And I'm going to specialize in the case of 1/2 electron per unit cell. And we prove what I call physicist theorem, that the ground state degeneracy of any quantum charge liquid is at least 8 when you have 1/2 electrons per unit cell. And if the quantum charge liquid preserves time reversal symmetry, I guess I forgot to mention that I'm assuming the Hamiltonian that begin with has time reversal symmetry. There's no magnetic field, basically. Then the ground state degeneracy has to be 16. That's a minimum number they can possibly have. Now, even better, if you find exactly 16-fold ground state and there's no symmetry breaking of any kind, then we know exactly what it is. There's a unique class of quantum charge liquid, a preserved time reversal symmetry and with this number of ground states, known as a Z4 gauge theory. And there's, all of this can be generalized to other fractional fitting. Okay, so this gives you a set of bounds. For example, if you see the number of ground state is below 8, then you know the time reversal symmetry and lattice translation, time reversal symmetry have to be broken. And if you see somewhat between 8 and 16, well, then you know, well, okay, so if the degeneracy is below 8, then you know lattice translation must be broken. If it's between 8 and 16, then at least you have to break one of these symmetries. All right, so let me just quickly describe what this state looks like, or at least a kind of pictorial way to think about this quantum charge liquid. So to just have a picture of what's happening, not proposing a microscopic mechanism for the state, is just a kind of a pictorial description of the state. First, you want to imagine the electrons, they form Cooper pairs. Okay? So they form these kind of molecules, bosonic molecules. But then the molecules, they fractionalize. So what that means is that they are no longer the elementary excitations, not even the electrons, but these 1/2 charge particles become the elementary excitations. So one Cooper pair kind of splits dynamically into 4 elementary particles, each of which carries 1/2 charge. And in order for these particles to keep track of where they come from, they have to be charged under emergent gauge field, which acts as kind of glues to put them back into Cooper pairs. Okay. So this is a kind of pictorial way to think about this minimum charge liquid. All right, you might be wondering where all of these come from. I won't be able to tell you the proof, it's too long, but I try to sketch some ideas. Okay? The idea is to really take advantage of these kinematic constraints as much as possible. So here we have translation symmetry, we have charge conservation, and we have the fitting condition. Okay? And of course, just based on these is not enough. We also need to a little bit more about how to describe these 2-dimensional gap faces mathematically. And it turns out that's an anion theory. So essentially, we need 2 inputs. Each of them, one of them is a generalization of the Laughlin's argument to this problem. And the other one is to really kind of use this 1/2 fitting condition. So each of these arguments gives us a particular anion or particle in this theory. Okay? And also tells us some of their properties, the charge they carry and their braiding statistics. And then we can kind of just run with this set of particles and constrain the theory as much as possible using mathematical consistency. From then on, you don't really need to think about any of these microscopic conditions. They are all kind of captured by these 2 observations, and then you can just kind of try to constrain it using consistency, okay, and arrive at the condition that I told you. Okay, so this is the first story of using these kinematic constraints, anomalies, to constrain what can happen for example, in the interacting electrons. All right, so we can apply these ideas to other systems. You don't even need to start from anomaly. You can start from, for example, some knowledge of Hall connectivity. Okay? And you can also do this in 3 dimensions, and we have constructed minimal gap faces with discrete chiral anomalies, which might be relevant for wire metals. It's work done with Xinping in the audience. All right, let me pause and see whether there are any questions about this part of the talk. Yes.
Do you have an example of a microscopic Hamiltonian for the Z4 gauge locally?
Yes, so you can construct Hamiltonians which realize this is ground state, although that's not a very realistic Hamiltonian. It does have local interactions.
So what's Like, I understand why you need here to do electrons in a molecular pair, but how do you get medium executions? Like, what's the interaction with it?
So the interaction that favors this, it really now, so I don't really have a general sort of mechanism to favor this particular fractionalization. Okay? It's just the way fractionalization is the only possible way to get this quantum charge liquid if you start from full pairs. So this kind of argument tells you, what it has to be, okay? Although it doesn't really says how you're going to get there. All right, so let me now move on to my next story in the same sort of umbrella. I'm glad that my Zoom hasn't been making any noise. So this time, I'm going to apply it to a very different context. It's not even about ground states. So far, we've been thinking about ground states. But now I'm going to think about what happens at finite temperature. Okay. So of course, we know from STEMAC that once you couple your quantum system to a thermal bath, it's going to thermalize, and it's going to describe by a Gibbs ensemble, the canonical ensemble. The density matrix of the system is no longer just a wave function, so really the density matrix, and the density matrix is given by the famous Boltzmann or Gibbs distribution, e to the minus beta h is Hamiltonian, and beta following the standard convention is 1 over kBt. So we often associate finite temperature or thermal effects with classical world, right? So we are at room temperature, and the world appears very classical to us. So that's a sort of a common intuition. And the question I'm going to ask here is how quantum can thermal states be? Are they all always somewhat classical? Of course, I need to really define it sharply, what I mean by a quantum and or classical. So here's a definition inspired by what you see in classical STEMAC. So if a thermal state is classical, it means that you can represent it, at least in some basis, as an ensemble of short-range entangled pure states, maybe up to some finite depths deformations. And if that's the case, then we say it's classical or trivial. Essentially, in this case, it kind of looks like a classical STEMAC. So agree with our intuition. And surprisingly, this was the only reference I know is a result, a paper this year, that if sufficiently high temperature, you take any local Hamiltonian, quantum Hamiltonian, this state is classical in this sense. And you can also prove that in 1D, in one dimension, all the thermal states are classical, or in 2D, many known cases are classical. So it's basically all I'm saying that in all the cases that have been looked at, they appear to be just classical. So I'm going to discuss one example where this is not the case. This is an example of a long-range entanglement, somewhat surviving finite temperature in 3 dimensions.
So Meng, in 2 dimensions, it could be that there are non-trivial states at non-zero temperature, but we don't know.
That's possible, although we don't know any example. There's no general proof yet. Although Hastings has a proof that for all commuting project Hamiltonian, these states are classical. Okay, so I'll call this thermally stable logical state. And here's a Hamiltonian, so I'm not inviting you looking into Hamiltonian. They are made small on purpose. But 2 things that I just want to mention about this Hamiltonian. So it is a Hamiltonian, the concrete, each term is local, it involves some number of spins on a cubic lattice. Okay? And there's a spin model, so the degree of freedom are qubits, basically. And this model is exactly solvable, so you really know everything. It's a representative of a family of models which share this property. And I'll just denote rho as a density matrix. So this model is called a twisted toricode. And here's a kind of a picture that I want, a phase diagram, sort of. So there's some temperature T of 0. Okay? So first, at 0 temperature, this is an example of a topological order state, which has 8-fold ground state invariance if you put it on a 3-dimensional torus with priority boundary conditions, and you can use it as a quantum memory. So t equals 0 is definitely interesting and non-trivial, but this non-triviality somewhat persists to some finite temperature, T of 0. T of 0 we can calculate, although it's enough to know that there's some finite number that below which the state remains non-classical, long-range entangled. Okay, so why is this the case? Well, again, I won't be able to give the full proof, but I try to kind of illustrate the main sort of features. So in order to understand what's happening, we need to think about excitations of this model. Okay? Because it's exactly solvable, we really can understand everything about the entire spectrum, not just the ground state, everything about the spectrum we can understand. And excitations come in two varieties. The one type of excitation has energy concentrated at one point in one small region, and you can say that this is kind of like a particle. Importantly, this particle is a Fermi. If you exchange two of them, you get a minus. And the other kind of excitation, a different kind of excitation, has energies concentrated along a line, along a loop. I'll just call it a loop. And if you move this particle around the loop, you pick up a minus. So this is what excitations look like in this model. And for thermal state, of course, we know we just have a big mass of all the loops and particles distributed in some random way. And the energy probability of such a state is given by the Gibbs factor, the Boltzmann factor.
There's static, right? There is no kinetic energy. So
yeah, because it's exactly solvable model. All of these are static item states. They don't have dynamics. Although you can add dynamics, a little bit dynamics, and nothing's going to change.
when you're trading,
Can we use a mic or?
Oh, yeah, sure. So the question was, no, these are these static excitations which do not move at all. So in this particular, for this particular Hamiltonian I wrote down, that's indeed the case.
so by threading one particle around another, you do a sequence of unitary transformations.
So yes, so when I say moving one around another, I just basically I do a sequence of unitary transformations to accomplish that movement. But if you do have some dynamics, then this can happen adiabatically. Then it's a statement about adiabatic motion of a particle around a loop that's fixed pin somewhere. Okay. Now, if you look at this Hamiltonian, there's no interesting symmetry except maybe lattice symmetry. Okay? But it turns out that there's a symmetry that's hidden there that requires some effort to be seen. So initially, we have just a mixture of states with different particle and loop configurations. And in particular, the number of loops is not conserved. You can have all kinds of different numbers of loops in this state. But what's quite interesting that when the temperature is below that threshold, you can remove all the loops, clean up all loops by applying technically a shallow quantum channel. So you can do certain quantum operations to remove all loops, to clean up all the mass until you get a state where all the particles are where they are, but the loops disappear. So what this shallow means is just that these two states have a large overlap. And you get a mixture of states with no loop at all. So now we uncover a symmetry where the number of loops is conserved. Okay? So this conservation is not the conservation of particles or charges, it's conservation of number of loops. And it's conserved trivially because there's just no loop at all. So number is 0, and that's also conserved. Okay, so the formal term for this fact is that there's an emergent two-form symmetry. That just means you have the conservation of number of loops. And this symmetry is anomalous because the symmetry is generated by the word lines of the fermion particles. So by moving a fermion around the loop, you know there's a loop. That's how you count the number of loops, mod 2. And anomaly comes from the fermionic statistics. If that doesn't really get very far, it's okay. We just need to know that the conservation is about number of loops. So now I can kind of sketch how the argument works. So first, by decoding, okay, basically, by removing all the loops, we can clean up the mass and get to an intermediate state, which exposes the underlying symmetry. And then using this fact that the number of loops is conserved and the particle is a fermion, we can show that this state is actually very far away from any sort of classical state or trivial state. And then you conclude that the state that we can start it with is also very far from that state just by triangle inequality. So this is example of a new quantum phase, as far as I know, that exists at finite temperature. And you cannot really think about it classically, as there's some inherent quantum correlations that persist even though you're heating this system up to some temperature. Yes.
How does T naught depend on? Does T naught depend on details or?
The T naught. So the question is, does T naught depend on details? Yes, it depends on the strength of basically the energy gap to create a loop. So that's what the T naught depends on. So I haven't, I skipped that detail. So there's some coupling constant in front of the various terms in Hamiltonian. One of them determines how much energy it takes to create a loop excitation, and that energy essentially determines this T. Okay, so in this case, it's somewhat different from the other example where we have symmetries in front of our face, right? There's charge conservation, lattice translation. Here, the symmetry is somewhat hidden, and you have to do some work to decode that symmetry from a huge mass of particle loops. But when you see that, it tells you immediately that the state is really quantum or long-range entangled, even though it's a finite temperature state. All right. Any questions? Yeah, Shankar.
What is your diagnostic here for non-classical?
So that's a great question. So the one way to see that it's non-classical is, well, the way that we show it is to use this anomaly symmetry. Because anomaly, basically, the general law is that anomaly forbids having a trivial state. And the state, this one, has anomaly explicitly. So this one cannot be trivial, and this one is very close to that one. So that one is also not classical. So that's how we show that. That's how we diagnose non-classical ness of the states. Steve.
So you have periodic boundary conditions.
Right.
If a loop runs from one boundary to the other,
right.
Does it have infinite energy and from it?
Yeah. So now remember to repeat the question. The question is, if you have a periodic boundary condition, if you have a loop running from one boundary to another, does it have infinite energy? So if we take the thermodynamic limit of that length goes to infinity, indeed the loop will have infinite energy because the energy of the loop is proportional to length of the loop. It has some finite energy per length of tension. But that's a common for loop excitations in this kind of three-dimensional systems. Itself doesn't really mean.
Maybe the free energy.
Yeah, so that's why you have a T0 because of the entropy computation between energy. So at low energy, low temperature, you don't really have long loops. That's why you can decode them. Yes.
So in terms of the second question about the diagnostics.
Yeah.
Is there any response function that could be different?
So the only response function that I can think of, because this system lacks any symmetry, basically. In order to see this, you have to decode. So this one symmetry that you can, one kind of response or correlation function you can try to measure is putting a string operator for these fermion particles and see that it has expectation value that doesn't decay with the separation of the two bonds. However, there's a caveat because if you try to do it here, you see that this correlation is messed up by the loop excitations in the middle, so you don't see anything. So you have to somehow first get to this state by doing a classical computation, and then you can measure. But that's a great question. It'd be interesting to figure out what else response or correlation function that one can consider to expose this long-range entanglement.
Local correlation functions of local operators don't distinguish.
Don't distinguish. Right. But that's almost true in every topological state. And that's, so before I move on, I'll just say that this is one example of something I've been thinking about in the last couple of years of new sort of quantum phenomena in many-body open systems in both 1 dimensions and 2 dimensions. And I'm happy to talk about them offline. All right, so I've discussed 2 examples of using anomaly to kind of constrain and uncover interesting physics. And now I'll move on to the next part, which actually exactly Nick's comment was exactly the reason that I like to think about this. That local correlation functions don't distinguish this kind of stuff. Okay. And just to be specific, let's start from this type of state where there's a gap. Okay. And we know it is difficult to tell apart these distinct phases from local observables, local correlation functions. Exactly the reason why people used to believe or still believe flat Earth. Yes, the main problem is not that they believe flat Earth, but they fail to recognize that Earth could be a torus if you only measure locally. So non-trivial states are non-trivial, but it is difficult to tell that from local measurements. All right, and you need something non-local to distinguish them. So one example will be topological entanglement entropy. Okay, but from that word, you probably already recognize that that's not a physical observer. So you take some region, measure its Von entanglement entropy, calculate or measure numerics, and then from that you can figure out some constant which can possibly which may distinguish different phases. But that's just not a physical observer. This is a Von entropy of a reduced density matrix. Okay, so we like to have something that's in principle observable, even though it might be very difficult with current technology, but in principle observable that can tell apart different phases. Okay. And again, I'm going to start from an example where the system conserves some charge Q. And assume that there's no symmetry breaking. So if you choose some region A, this is just some region in the system, and I'm going to just talk about 2-dimensional systems for now. Choose some region A, Q of A counts the number of charges, total number of charges contained in that region A. So even though the charge is conserved, meaning that the total number of charges in the entire system is conserved, is a constant, but if you look at part of the system, it's not conserved. This quantity has quantum fluctuations. So we can measure the fluctuations, but just by computing the variance. And this is the average of Q squared minus the square of the average. And here's the average always defined with respect to the ground state. And we will be interested in what happens in the large region limit. We take the large system and then look at the large region. And I will explain in a minute that this quantity under these assumptions will scale as linearly with L, but with some constant corrections. Or you can consider higher moments of the charge fluctuations and they have similar behavior. Okay, so why does this quantity scale at least to a leading order in L as a linear function? Well, for the following reason, simple reason. If you have motions, obviously the fluctuations come from motions of charge. But if you have a charge that's kind of just moving inside this region, it's not going to change the number of particles, the number of charges inside Q, inside A. So any process like this does not change Q of A and does not contribute to fluctuations. The only way that you can change the number of particles, a number of charges inside A, is to hop one out from inside to outside. Okay? But because the Hamiltonian is local, all the physical processes are local, this can only happen very near along the boundary of A. So the kind of total contribution of all such processes have to kind of add up to proportional to length of this boundary, because that's the only place where Q of A can fluctuate. Okay, so with that in mind, Now, let me just kind of make it a little more systematic by defining the generating function. So from this slide on, I assume that we normalize Q of A, so the average is 0. I don't have to worry about the average. And then we can assemble all these higher moments of the charge fluctuation into the generating function in this way, where here is theta is some parameter. And you can convince yourself from similar arguments that I just showed on the previous slide that expectation value of this exponential of I theta Q of A is going to decay exponentially with L. That's for the same reason that the Q square grows like L, but with some constant prefactor that multiplies the exponential decaying function. So this part is not quite interesting. That's just generically what happens in the system with local interactions. What's more interesting is this constant P in front. And this constant P, if you have a gap state, is insensitive to the shape of A. No, it doesn't really matter. You take a circle, you take a discrete region, or you have some weird region, you're going to see more or less the same number in front. Okay. And another reason to write it in this form is that you can now recognize that e to the I theta q is basically the U1 symmetry transformation, okay, generated by a charge Q. And what this e to the I theta q of A means is that we restrict the transformation to the region A. And now you can take any global transformation, symmetry transformation, internal symmetry, and truncate it to some region and put it here, and you have a similar relation. But the constant will be different.
LA was the linear size?
Linear size.
Not the
Right, the linear size. Or if you like, the parameter of the boundary.
2D.
This is 2D. Yes, this is 2D. Okay, so just to give some examples of what this number tells us, let's just do a calculation in a train insulator. It's also called the integer quantum Hall or quantum anomalous Hall insulator. It's, for this purpose, they're all the same. Okay? And it's a gap state with a quantized Hall conductance. And let me just fix it to be 1 in the unit of E squared over H. Okay? And has a chiral fermion running on the edge. So if you do this, if you just go and calculate, because this is the free fermion state, you can calculate anything you like. We'll find that this d of theta takes this somewhat peculiar form. It's equal to 2 when theta equals pi and 1 otherwise. This shows that there's some reason to consider the general theta, because you won't be able to see this 2 if you just expand it as a function of theta. To Taylor expansion, you never see this. And this is also true regardless of the strength of interaction, as long as we stay in that space. Okay, so the next example is a topological superconductor in 2 dimensions, which has quantized thermal Hall conductance instead of electric Hall, and the chiral Majorana fermion on the edge. So it's a superconductor, charge is not conserved. Okay, but again, because the superconductor, the charge mod 2 is conserved. It's only the Cooper pairs that are fluctuating. So the even oddness is a well-defined quantity for superconductor. And we can ask what's the parity of the number of fermions inside the region. Again, decays exponentially, but with a somewhat funny square root 2 factor in front. And this square root of 2, for those who are familiar with the physics of topological superconductivity in 2 dimensions, is a dimension of Majorana zero modes in the superconducting vortices. This is not a coincidence. This is actually the general result, where this factor d somehow counts the effective number of degrees of freedom for a symmetry defect. So this is the meaning of d. So the bottom line is that d is a quantized invariant, which you can relate it to some inherent topological properties of this phase element. All right. So I'll use the rest of the time to briefly discuss what happens at criticality. But let me first pause here and see whether there are any questions. Yes.
So this expectation value, do you have any experimental observable in your minds, where how these can be measured?
Well, so unfortunately, this is the general e to the I theta q is very difficult to measure. Q square, it's essentially just another way to think about 2-point functions of q. So that can be measured. Okay? So q square, it's really just if you write it out, it's an integral of equal time charge density correlation function.
So, spatial resolution, I guess.
Sorry?
So assuming you have access to some spatial resolution.
Right. So this is what's interesting here is the large distance behavior, not what happens at very short distance. So the resolution, the limit of resolution would be from like a small momentum and small frequency. Okay. But in some beyond solid state systems, in some other systems where you can actually count the number of particles, then this is actually measurable, such as cold atoms or Rydberg arrays. Okay, so lastly, let me just discuss what happens if you move away from this realm of gap state, okay, to quantum criticality. This is the point where the phase of matter suddenly changes, a continuous phase transition. And at this point, there's a much richer dynamic. So dynamics in the gap space is somewhat simple. There's not really much going on at low energy. But quantum critical point has a lot of stuff going on at low energy. There's gap excitations, and the correlation functions of local observables already decay as a power law with distance. Okay, so now if you go and do this, we'll find much richer behavior because of all of these gapless excitations. The excitation value of this operator will now know about the geometry of this region, not just the size, not just some constant, it actually knows about the geometry. In the extreme case, when you have a region like this, a rectangle region, which has sharp corners, then this quantity will again decay exponentially. This is just everywhere, and it's not very interesting. But now the prefactor is no longer constant, but it's the power law of the size of this, the linear size of the region. And exponent here can be considered as a new type of critical exponent associated to defects. And more generally, this number will depend on the opening angle of this cone.
You compute it on the gapless boundary of a gap state, will it take the same form?
Well, all that matters is what the low energy theory. So the gap bulk will not contribute if you just do it on the bound. Okay, just to show that we can actually compute this and do something. You can do this calculation and do some fitting to figure out what this S is, and agrees well with the theory. Now, I'll end with application of this kind of disorder operator this is sort of a numerical experiment. We don't really have a good explanation of what happens at a peculiar transition called the confined quantum criticality. It's a Landau forbidden transition between two different symmetry breaking states. Such a transition is difficult to describe within the kind of a standard Landau theory. Okay? But there are scenarios proposed in the past where this transition can take place. And there are lattice models, spin models, and fermion models, which presumably realize this transition. So we go and calculate this quantity. Well, what's important is the contrast of what happens near theta equals pi from the previous figure where the curve contrast goes up. But in this case, the curve comes down, okay? Which means the S becomes negative near this large angle theta, and also here in a very different model. So what's the significance of this sign of S? Well, it turns out that if you assume that this transition is described by a unitary conformal field theory, with that assumption, then this S cannot be negative. S has to be positive. So this is impossible in a unitary theory. This means the low energy theory of this transition cannot be a simple unitary conformal field theory. All right, but we still don't know the origin of this negative sign. And, this is an example where the disorder operator exposes something about the confined quantity effect. Okay, so I guess
2 plus 1 dimensional conformal field theory.
yes, this is 2-dimensional spatial lattice.
2 plus 1.
2 plus 1.
Why is the critical theory not a unitary CFT?
Well, so critical theory is not. So it doesn't have to be a true transition. It doesn't have to be a true continuous transition. That's one way out, is that you just have a very weakly first order transition. Or it's not a continuous transition doesn't have to be a conformal field theory. But we don't know. So this is just a numerical experiment, and we observe there's a negative sign that doesn't go along with a unitary conformal field theory.
And there's also some folklore that, you know, scale invariant transitions in unitary systems have to be conformal.
I don't think that's actually proving 2 plus 1. And here, so I think even in the case when it's proved, you also need more symmetries like Rorentz invariance in the relativistic field theory. This is a lattice model.
The effective theory, we still have Lorentz invariance.
The effective theory that's proposed has Rorentz symmetry, but we do not know whether the effective theory really describes this critical point. Okay, so I'll conclude, and most importantly, I'd like to acknowledge being really fortunate to to work with many brilliant students and postdoc and collaborators. So although I cannot put pictures all of them, so I'll just put those who have passed through Yale. Okay? And thanks for your attention.
For a very nice talk. Let's see, do we have any more questions? Yes.
So the computation that you showed just on the last slide for the deconfined criticality. So that's in the JQ model, lattice model, right?
So this one is a JQ model.
Right.
This one is a fermion model that's believed to realize the same transition.
No, okay, so S.
Have the door, please, on the way out.
The computation of S, so that's done with which model?
This is for the JQ model.
Okay, but can you compute S just in the proposed field theory itself directly?
No, because it's field theory, the proposed theory is strongly coupled. We don't really know how to do basically any computation in that
Okay.
field theory.
Yeah, thank you. Thanks.
I think there was a hand by Jack.
So in the part of your talk where you're describing a phase that persists up to some non-zero temperature with loops and fermions that emerge, this was the consequence of starting with a cubic lattice with spin 1/2 on each site and picking a certain bunch of Pauli matrices to connect them. Is that correct?
So this is the consequence of having the Hamiltonian having certain structures.
Yeah. So what I was going to ask is, you showed this very funny, arrangement of different Pauli matrices,
right,
connecting the nearby spins. Right. What is it about that microscopic Hamiltonian? Is there some qualitative feature that gives rise to this interesting phase?
Try to go back and see.
Or is that kind of a one-off?
So the feature of this Hamiltonian, you can see that. Okay, so if I want to say something about the general feature of Hamiltonian, the first of this term imposes some kind of gauge structure at the microscopic level. Okay? And then the other term is kind of like a Maxwell term for the gauge field, but it's a funny one because if you don't just have the blue ones, this will be the Maxwell term, the standard Maxwell term for Z2 gauge field. But now we attach all of these red edges so that the particle becomes a fermion, basically.
Okay, thank you.
So any Hamiltonian with this kind of structure would have similar behavior.
One last question from Steve, and then.
So in the, not this microscopic Hamiltonian, but the pictures you drew of fermions and loops.
Right.
I mean, can I make an effective theory that has like a Bose condensate below, that's has long range order, so the vortex loops are small, and somehow couple fermions to those and get some equivalent model
You
to.
want to think about the situation where the loops become small. Or
Yeah, so if you're in a superfluid phase, the
Right.
loops have to be small, the vortex loops.
yeah, so in a sense, this is already in some sort of superfluid phase, right? The fermion is Z2, so it's kind of like a superconductor, effective zero superconductor. But no, the Z2 from parity is gauged. But you cannot really further condense these fermions.
No, but if there were another boson field,
Okay.
whose vortex loops were those blue things?
I see. Okay, okay.
Yeah.
Right. So as far as I know, the consistency of this kind of gap space in 3 dimensions doesn't allow a charge that sees loop as a pi flux to be both bosons and fermions. It's either bosons or fermions. You cannot have both.
Okay.
And if you replace this with a boson, then all of this goes away.